My name is Tom Christ, and I'm going to talk about scaling our data systems at Tumblr. First, an introduction to Tumblr, if you're not familiar. Tumblr is a social blogging platform designed to enable people to share various types of content easily and quickly. At the bottom of the screen, you can see the icons for the different post types which make up the different content types on Tumblr. At the heart of Tumblr are the blogs. These are the basic building blocks of all of Tumblr. This is an example post from my blog of the New York skyline. All content on blogs and all social interactions are keyed to a specific blog. This means that this content can be easily grouped together on a single cluster of databases. The presentation of the blog is not personalized or customized based on the viewer's preferences. This means that these blogs can be linearly scalable and are easily cacheable. Things become more complex when you view Tumblr through the dashboard. This is a collection of the blogs that you follow, ordered by time. It's a personalized feed from an arbitrarily sized asymmetric graph, meaning that all the blogs you follow, we look up the ones that posted most recently, we create a list of their posts and sort them by time. This data is very time sensitive. Because of the creation rate and because of the user experience, it's very difficult to cache. In fact, we don't cache the dashboard at all. All blogs go to a central store. This is the group of shards that I referenced earlier. We have a global list mapping Tumblr logs, post, and publish times, which we use to aggregate these posts into a feed and sort them. Some of the implications of this behavior are that the post index must be sharded by time, and every view of the first page must go to the most recent post index database. We keep a record over all of time of all the posts that were created for all blogs, but when the dashboard first page is loaded, that must go to the most recent post index database. This creates a migrating hothead of data. That means the most recent data, posts created over the past day or two, are the most active and see the most access. In addition to this, posts remain mutable forever and can never enter a read-only or cold storage mode. Some stats to frame the challenges and define the scale that we operate at. Tumblr is top 15 in US reach. We have over 20 billion page views a month. Our peak page view frequency is approximately 75,000 a second, and our peak post creation rate is approximately 4,000 a second. This adds up to 70 to 85 million new posts per day, with 65 billion posts and 144 million blogs. Our data growth rate is fairly substantial as well. Between 2012 and today, we grew from 31.5 billion rows, adding up to 13.5 terabytes, to 229 billion rows, adding up to 54 terabytes. This is all stored in MySQL, and this only counts for production data. This does not include replicas, scale-out reads, or for redundancy. This is the working set of data at Tumblr. We define our different data problems in three ways. There's low latency, high frequency cache data. There's offline throughput batch processing. This is essentially Hadoop and the Hadoop family of technologies. And there's our production data store, which is MySQL. This is the canonical source of truth for all data systems at Tumblr, and the source from which all data flows. Our high volume, low latency story has two chapters. The first is Memcache. This is a fairly common technology, widely used in internet applications. It's a key value in-memory data store, which we use as a write-through cache. We have about 9 pools consisting of approximately 100 servers, which equates to approximately 5 terabytes of data. This is the working set for Tumblr. This is the data which is most recently accessed, most recently edited, and is currently in use. At peak, our Memcache installation does approximately 2 million queries per second. We have a very high cache hit rate, and it's really what allows us to scale up our reads. We cache all active entity data, so all posts, users, blogs, and various other pieces of information about the site, as well as relational data. An important thing to note about our caching scheme is that relational data, such as data about blogs you follow, the list of blogs you follow, and the list of blogs that are following you, and similar data, only stores identifiers. We don't cache lists of entities. This does mean that we have to perform an additional lookup to retrieve entity data. However, it also makes cache invalidation much simpler and prevents us from having stale data. Another low latency store we use is Redis. We have an in-house proxy called Rediscover, and we use this primarily for set-based logic, for operations such as retrieving data from sorted sets by score, intersecting sets, performing set unions, and other set-based operations. We have approximately 9 pools, which do approximately 160,000 queries per second at peak. As I mentioned before, our large-scale batch processing is primarily predicated around Hadoop. We use many of the Hadoop family technologies, such as Hive, Pig, HDFS, HBase. Our largest cluster is approximately a 3 petabyte Hadoop and Hive cluster, one of several that we maintain. It grows at terabytes a day and consists primarily of data exported from MySQL via Scoop, as well as custom logs pushed out through Scribe. We periodically export data from our production MySQL servers on a nightly basis into HDFS and then perform analyses and similar operations on it. This is a broad illustration of how these systems interact. Our application servers, including web application servers, services, and Gearman, push data through Scribe into HDFS, or into HBase, which is then consumed by a variety of MapReduce and cron jobs. These perform things such as aggregates, counters, rollups for analytics, custom email content, which is then pushed to our primary data stores such as Memcache, Redis, and MySQL. This is then consumed by the application servers, forming a circle of data at Tumblr. These are some of the tasks we run: business intelligence, identifying trends and usage, looking at how people interact with each other, examining the social graph at Tumblr, spam detection, looking at accounts which exhibit spammy behavior. This could be creating a large number of secondary blogs, or following a large number of blogs within the same second, or being followed by a large number of blogs in the same second. These are all behaviors which are suspicious and warrant further investigation. The basic idea behind spam detection at Tumblr is to assemble a heuristic and then establish the thresholds within which a normal user will exist, and then take a closer look at blogs which fall outside those ranges. We perform advertiser analytics, create personalized email campaigns, as well as calculate and publish search rankings and weightings and personalized search data. This is an example of one of our business analytic analyses. We analyze users by their registration date and their last activity, and by that, we group them into buckets. This is how we calculate our monthly active users and how we categorize users based on their activity. Based on these categories, we can then decide whether we want to reach out to them via email and what content to publish in that email. This is an example of a personalized email that I received. They will analyze the people that you follow, and then the blogs that the people that you follow, calculating the intersection, as well as the score that those blogs have with relevancy to your interests. They'll then offer suggestions to follow, and we push out personalized emails, several hundred million a day, in order to promote engagement and to try to retain users. This is an example of a search result. We perform batch operations which calculate scores, which publish those scores, and publish and help determine personalized search rankings. A key part of data at Tumblr is MySQL, and what's core to that is automation. At Tumblr, we have 276 plus dedicated MySQL servers, including replicas and active and passive slaves. We have approximately 229 billion rows, adding up to 49 terabytes of data, and 2 dedicated engineers to our MySQL installation. Our automation is a leverage point, which allows us to have a low head count, but still enable us to perform at a high level, delivering microsecond guarantees for query response time, as well as linear scalability. Now, what is Jetpants? Jetpants is a command line suite of tools and programmatic library. This means that you can issue a number of commands on the command line for common tasks such as promoting service to master, cloning replicas, promoting replicas to receive read traffic, deactivating replicas, removing them from rotation, as well as destroying them, recycling servers, and all the sorts of day-to-day tasks you might expect from a MySQL installation or database management role. 2 primary points of leverage that we have and 2 very important things that we use to manage our MySQL installation are shard splits and shard merges. In addition to all this, Jetpants is open sourced and you can find it on the Tumblr GitHub page. A quick overview of sharding and how it relates to Jetpants and MySQL at Tumblr. When do you shard? You shard when application data becomes too big for one database. Now, there are a number of approaches you can take to solve this problem. You can apply a technique we call functional partitioning, which has various other names. You take related groups of data, related tables, data sets, and split them up and put them in different database clusters. And this works well enough, but what happens when a data set becomes too large for a single database? That is, at the most granular level, you have a single table, and then that becomes too large for a single database. At Tumblr, we apply a combination of functional partitioning as well as range-based sharding. We have functional partitions for data sets which require global lookup patterns. However, blog content, which is easily localizable to a single database, is stored in the blog shards. We use a range-based partitioning system, a range-based sharding system, instead of a modulo or hash-based system, for a number of reasons, some of which will become evident when I explain our shard split and shard merge process. However, for us, a shard is a continuous range of IDs for a blog. For example, here we have blog shards 1 through 49, 50 through 99, 100 through 149, etc. And this is how we divide up data, both to manage the data set size as well as parallelize writes. But what happens when the data set on a shard becomes too big for that server? That's when we leverage the shard split functionality of Jetpants. Here you have a shard which is IDs 1 through 99. Using the replica management features of Jetpants, we create 2 new replicas that are going to become the new masters of our split shards. we perform an export operation. Specifically, we do a select into out file using the range of IDs, which is going to be in the new shard. In this case, we're dividing the shard in half. However, there's no requirement to divide it in half. You can divide it into n number of shards, where n is the number of IDs. Once the export and import operation is finished, we then clone two new shards, or two new replicas underneath each new master. And you end up with a replication topology similar to this. All reads and writes in production are still pointed at the parent master shard. An important design consideration for Jetpants is that all operations, such as shard splits and shard merges, are completely reversible until production writes are going to the new masters. So in this case, we can back out of this operation, tear down these new shards, and then start back over in the case that anything goes wrong. If there's a data corruption, if a file copy fails, if data transfer goes wrong, these are all cases in which we can stop the shard split process, back out, and then restart. Once we've established this replication topology, we then go through a config deployment process where we point all reads for these new ranges at the new child masters, and then we point all writes for these new ranges of IDs at the child masters. We deploy the read config throughout the entire environment. This includes application servers, Gearman servers, and internal service nodes. And once that is completed and all reads are going to the new masters, we push writes out again through the entire application topology. This is entirely reversible even once reads go out until we start pointing production writes at the new child shards. Once we have done this multiple config deployment, multi-step config deployment, we can then tear down the replication topology between the old master and the new shards. And then we can recycle the original shard, leaving us with two split shards in production, and then the original shard being recycled and reclaimed for reuse in whatever capacity we see fit. Now that shard splits. However, what if you want to go in the opposite direction? There are a number of reasons why you might want to merge two shards. If you have hardware that's underused, if you are migrating to a new generation of hardware which has more capacity, if you're performing an operation on this shard which requires more room on disk, you can split the shard, perform the operation, and then merge the shard back together. This is if you need to perform a data transformation across your entire sharded data set that requires additional size on disk. This is a strategy you can employ. At Tumblr, we have approximately 70 shards. We haven't had to employ this strategy across all of them yet, but it's definitely something we're considering in the near future. In this case, you start with two shards, one with IDs 1 through 49, and the other with IDs 50 through 99. The end result of this operation is going to be one shard containing all records for IDs 1 through 99. We establish a replication topology similar to the diagram you see here. We perform a data export for the full data set on the source shards, blogs 1 through 49 and 50 through 99. We ship that data to the MariaDB nodes, to a MariaDB aggregator node, as well as the future master. Once that data is imported, we set up a multi-source replication stream from the MariaDB node to our standby slaves. We use MariaDB in this case before its multi-source replication capabilities. The rest of our topology at Tumblr is primarily Percona Server 5.5. Once the data import has completed, we set up the multi-source replication streams from the MariaDB to the source shards, which is aggregated together into a single replication stream. This is consumed by the future master. Again, in this state, this operation is completely reversible. If at any point any of these operations fail, if a validation step fails, if there's an error copying data, we can revert all this work up until we start pointing production writes to the merge shard. We perform a similar configuration deployment with the shard as we did with the shard split. We point all reads to the future master. Once that has been deployed across the entire topology, verified, we point all writes to the future master. And once that has been deployed across our environment, we tear down the replication between the servers. And we can recycle the original shards. An example of this that we used in production recently is we had a previous generation of hardware that we had migrated off of, but we had not altered the sharding ranges for those servers, leaving us with a set of shards which was at about 50% capacity. We performed a shard split on approximately every third shard of these about 12 continuous ID ranges, and then merged each half of the split shard into an adjacent ID range, leaving us with 2/3 of the shard count at about 80% capacity, leaving us room for growth, but allowing us to reclaim hardware and simplify management. Some takeaways. Cache everything. I can't stress the importance of an effective caching infrastructure enough. If one of our busier caching clusters has a node fail, we see approximately 300, 400, or 500% increase in query volume to our functional partition. Luckily, we have the overhead capacity to handle this, but the query volume in our memcache installation is high enough that we need that extra. It's what allows us to scale, basically. A second point is to leverage the strength of appropriate technologies. Memcache is excellent at highly concurrent sets and gets. Memcache is very effective at highly concurrent sets and gets. However, it does not support set-based operations. I think we've all seen implementations where you serialize a JSON array, shove it into a cache, take it out, deserialize it, and perform some sort of operation on it. What Redis allows you to do is to perform those operations close to the data. You can perform merges, set unions, intersections, and other similar operations. Also, invest heavily in automation. Not only is our MySQL installation heavily automated, all of our Hadoop, Memcache, Redis, our entire technology stack is heavily automated, allowing us to have a low staff count, but a high degree of effectiveness. You saw some of the numbers of the MySQL installation. and I'm one of 2 engineers that manages that topology. Having Jetpants as a tool to use and as something to lean on is incredibly important to maintain our effectiveness and to allow us to make forward progress in our environment. If we had to spend all day running around and putting out fires, we wouldn't be able to make much improvement in our technology stack. We wouldn't be able to research upgrade paths. We wouldn't be able to investigate application changes to improve query patterns. For example, the time that Jetpants saves us allows us to look at read queries. An example is there was a bad code path that was performing approximately 5,000 or 6,000 queries per second against one of our functional partitions. The source of this wasn't readily apparent, but when we tracked down the code path and eliminated the bad queries, it resulted in about a 60% reduction in select queries to that functional partition, which was fairly significant. Also, redundancy is key. You could see in a number of these diagrams that every shard has a master as well as 2 slaves. All of our functional partitions consist of a master, a number of read slaves, and a number of standby slaves. We use these standby slaves for offline operations, backups, the scoop job I mentioned earlier to export data to Hadoop and HDFS, and then just as well as redundancy. There have been a number of situations where we've seen multiple servers in a cluster fail. If 2 servers out of your 2-server cluster fail, you're in a bad state, and you'll see some sort of user impacting downtime. So we try our best to avoid that. There's a saying that goes, anything that's worth having 1 of is worth having 3 of, and that's what we try to apply at Tumblr. So that's an overview of MySQL Tumblr, and I'm happy to answer any questions that you might have.